A sealed tomb held a secret. It rewrites history. It's a discovery that exposed a lost science, a science of materials engineering. Ancient artisans mastered techniques we are only beginning to understand today. A single find dismantles our linear view of progress. It reveals a forgotten peak of human ingenuity. How did a blade resist corrosion for thousands of years? And what forgotten workshop lies hidden within a sacred resting place? What does it mean for our own civilization? When advanced knowledge can simply vanish from the world, the dust was just hanging there. It got into everything. We've been out there for weeks just working in the sun. The radar had given us a hint, just a small difference in the soil. It wasn't obvious. There was no marker, just the slow work of clearing things away. Then a trowel hit stone, but it wasn't bedrock. It was a cut block, a fitted stone. Everything got quiet then. We switched to brushes, and a shape started to come out of the hillside. A doorway. It had been sealed and then buried by a landslide covered in silt. The radar pointed us there, but the landslide is what kept it hidden. It was preserved. When we moved the first stone, air came out. Old, still air. It smelled like dry stone and something else, something metallic. We put lights inside. The walls, parts of them were reflective. They had a glassy sheen. That was the first sign. This wasn't a tomb. It was a workshop, a lab sealed shut. And the walls were telling a story in a material, a language no one's used for thousands of years. The light from our lamps hit something that shimmered, but it wasn't gold. It was a cooler color, a silvery gray. It seemed to take the light and give it back in a different way. This was the antechamber, the space before the final room, and it wasn't filled with wealth. It was filled with knowledge. The first thing we saw clearly was a dagger. It was on a low stone bench. The blade was flawless. After thousands of years in a sealed space, there was no rust, no green corrosion, not even a dull film. It looked like it had been polished yesterday. That was the first impossible thing. Next to it was a vase. It was so thin it was almost translucent at the rim. I've handled pottery from that period. It's sturdy, thick-walled, practical. This was none of those things. It was delicate, like an eggshell. But when someone tapped it with a fingernail, it didn't sound like clay, it rang. A clear, high tone. It hung in the air. That was the second impossible thing. And in the corners, near what looked like small braziers, were piles of a strange, glassy slag. It wasn't just debris. It had flowed and pooled. It suggested it had been liquid at a temperature ordinary fires can't reach. Each of these items, the untarnished blade, the singing vase, the mysterious slag, they were a statement. A declaration of mastery, a mastery our timelines say this culture shouldn't have had. We weren't looking at burial goods for luxury in an afterlife. We were looking at a curated collection, a collection of technical achievements. These artifacts were the primary texts of a science we didn't know existed, written not in words but in materials. The puzzle wasn't just what they were, it was how they could possibly be. That dagger was the center of it all, sitting there on its pedestal, and it broke the most basic rule of what iron is. Iron rusts. In a sealed space, with just a trace of moisture over centuries, it should have been a crumbling orange stain. But this metal was perfect, a mirror. The first tests were non-invasive, just a handheld scanner reading the surface chemistry. The results came back and they didn't make sense. It wasn't just iron, the composition was complex. There were traces of nickel and chromium. And if you know anything about metals, those two words together, they ring a very modern bell. That's the signature of stainless steel, a material that changed everything in the early 20th century. To make it, you need precise chemistry and temperatures over 2,000 degrees. We tell ourselves a story of linear progress. From bronze to iron, then after a long time of simpler work, we learned to make steel and then finally stainless. This blade, sitting in silence for it, cuts that story in two. It's an artifact outside of its time. So the question changes. It's not what it is, but how it could be. How do you create a uniform alloy, mixing metals evenly, without the blistering heat of an electric furnace? How do you even know to add chromium, an element that in its raw form doesn't look special? This wasn't an accident. You don't stumble onto stainless steel. Those specific elements in those specific proportions, they point to a deliberate recipe, a formula. It suggests generations of experimentation, trial and error in some lost workshop where artisans weren't just making tools, they were exploring the nature of metals. They were engineers. This one blade makes us reconsider an entire era. It whispers that a peak of materials science was reached, and then that knowledge was sealed in a tomb forgotten. What else did they know that we've had to painfully learn again? To feel that blade's weight, you need to go back to the world before the tomb was opened. Historians had mapped it all out. This was an age of kingdoms, trade routes, early writing, monumental architecture. And in technology and making things, it was the age of bronze and iron. You picture the smith at his forge. A simple clay furnace, charcoal, leather bellows pumping air to raise the heat. It was powerful, revolutionary. It could melt copper and tin into bronze, a metal strong enough for weapons, for tools that shaped civilizations. Later, with more effort, higher temperatures, they learned to smelt iron from ore. That iron was valuable, but it was brittle, full of impurities. It took skillful hammering, reheating, forging to work it into something useful. That was the ceiling, the accepted limit. The tools were fire, air, stone, human ingenuity. The temperatures they could reach, while impressive, had limits, enough for the metals they knew, but far below what's needed for truly homogeneous alloys, for more stubborn elements. The knowledge was empirical, passed from master to apprentice. It was about the feel of the heat, the color of the flame, the sound of the hammer. It wasn't, we thought, a science of microscopic structures, precise chemical formulas. That's the context. And against that backdrop, simple forges, hand-hammered iron, finding a corrosion-proof alloy isn't just surprising. It's anachronistic, like finding a pocket watch in a dinosaur fossil. The object doesn't just add a new item to the past. It shatters the entire shelf we built to display that past. It forces a question. A humbling one. If our understanding of their limits was that wrong, what else have we underestimated? Their world, their capabilities, their daily life. The sealed tomb didn't just preserve artifacts, it preserved a contradiction. A silent challenge to the narrative we had written for them. That blade was asking something, and the answer is in one idea. They weren't just using materials, they were engineering them. We have a field for that now, materials engineering. Scientists don't just take a piece of metal as it comes, they look at its microscopic structure, they change its recipe, they control how it's heated and cooled. To give it specific properties, to make it stronger, or lighter, or resistant to corrosion. It's designed, but at the smallest scale. And the evidence from that workshop says these ancient artisans were doing the same thing. They were proto-engineers, they didn't have electron microscopes, their laboratory was the forge. Their method was trial and error, generations of it. Think of a master potter at the wheel. Their hands feel the clay, they know the pressure to apply. That's an empirical science. Knowledge written in the muscles. Now take that understanding and apply it to matter itself. The singing vase, that ringing ceramic, ordinary clay is porous. It's a sponge microscopically. To make it thin and strong and resonant, you have to change that. You need clay. You need to control the firing temperature with precision. You might use a glaze that fuses with the body, sealing it. That's not just making a pot. That's manipulating the material's internal architecture for a new function. The beauty was a byproduct, a technical triumph. Then the slag by the brazier, that glassy substance. To create that, you need sustained, intense heat, which means they weren't just burning wood. They might have used forced air drafts, special bellows. They were engineering the combustion process to reach temperatures that could melt stone into new forms. That's the pursuit of a new state of matter. And the dagger, the alloy. Mixing iron with nickel and chromium isn't an accident you make once. It's a recipe. Discovered, refined, recorded. They learned that by adding certain ores to the melt, and by controlling the cooling, maybe quenching it in a specific liquid, they could lock in a new property. A property we call stainless. That is the heart of materials engineering, taking base substances and transforming them through knowledge and process into something nature never made. They saw potential in raw earth and rock, and through their art they unlocked it. This lost science wasn't abstract theory. It was a hands-on wisdom. A dialogue with fire and earth that achieved results we struggled to explain. So what happened to that conversation? Why did it go silent? They combined metals. They didn't just find them and use them. They mixed them. That's the first thing we see from the workshop, alloying alchemy. In the residues, in the small ingots, it's clear. This wasn't contamination from a dirty crucible. It was consistent, purposeful. They knew what they were doing. Bronze is the common one, copper and tin. But here the story is more nuanced. They weren't just making bronze, they were engineering it. The analysis shows copper combined with specific measured amounts, arsenic or tin. They did that because each recipe created a different property. A little more arsenic might yield a harder, more brittle alloy, good for a chisel that needs to hold an edge. A little more tin might create a tougher, more malleable bronze, ideal for a hammerhead that needs to absorb impact. They were creating grades. Different tools for different jobs required different materials. That's a staggering leap. It means they understood through observation that the whole could be greater than the parts. That by introducing a tiny amount of a foreign element, they could command a drastic change in the material's behavior. That's the very heart of modern metallurgy. It's why we have thousands of specialized steels and alloys today, each for a specific purpose, from watch springs to spacecraft skin. They grasped this concept. They applied it with a precision that speaks of recorded knowledge. It was a science of recipes, a cookbook for metals. The goal wasn't just to make something. It was to make something exactly right for the task. This purposeful blending hints at a deeper understanding, one that moves beyond utility and into prediction and control. It suggests they could look at raw copper and not just see a metal. They saw potential, a palette of possibilities waiting to be unlocked through combination. And if they could engineer bronze with such intention, what other combinations were they capable of creating? The second principle is right there in the slag. That glassy stuff by the furnaces, it's a record of temperature. It tells us they weren't just getting things hot. They were controlling the heat with a rhythm, a repeated sequence, heating and cooling over and over. That's thermal cycling. It's a powerful tool in materials science. It's how you speak to the metal's inner world, its crystalline structure. When metal cools from a liquid, its atoms form tiny grains, like a mosaic. If those grains are large, irregular, with gaps, the metal is brittle. It has weak points, it cracks. But if the grains are small, uniform, tightly locked, the metal becomes tough, resilient. It can bend without breaking. So how do you do that? You don't just cast it, you work it. You reheat the solid metal, not to melting, but to a specific color. A precise temperature where the atoms can move again, but the structure holds. Then you cool it. Maybe plunge it into water or oil. That's quenching. It freezes the structure, creates hardness. But that hardness can make it brittle. So you might heat it again just a little to relieve the internal stress. That's tempering. Each cycle changes the material. It's a conversation. Heat, cool, hammer, heat, cool, hammer. The evidence from the workshop metals shows these exact patterns. The grain structures are refined. They show signs of repeated working. So the artisans knew the final shape was only half the battle. The true mastery was shaping what you couldn't see, the internal architecture. They were performing microscopic surgery with fire and hammer. This knowledge wasn't in equations, it was in the hands. A master smith knew the color for annealing. He knew the hiss of the perfect quench. He knew the ring of the hammer that meant the grains were aligning. This was a guild secret. Passed from teacher to apprentice over a lifetime. A practical, tactile science of how temperature shapes destiny. To hold a blade they made was to hold a material that had been through a transformation. Not just of form, but of essence, stressed, softened, hardened, balanced. A material taught through fire how to be its strongest self. This principle moves us from combining ingredients to training the material. It reveals a philosophy that strength isn't a gift, it's a process, a journey through the flames. The third principle is visible, it's a story on the surface. When you look at the dagger, the vase, the tools from that sealed space, their surfaces show intervention. They weren't left as the furnace made them. They were changed at the outermost layer. This is surface modification, a final, deliberate act. Think of it as armor, a shield applied at the molecular level. On the metals, especially that blade that didn't corrode, analysis showed something. It wasn't just the alloy underneath that was special. Its skin was different. There's an ultra-thin, stable layer, a coating bonded to the metal itself. How do you create that? One method ancient cultures used was a controlled chemical bath. Dipping a finished blade into a solution from plant matter or mineral salts. That wouldn't just clean it, it would start a reaction. The metal's surface would transform into a hard, glass-like oxide. This layer is passive. It doesn't react with air or moisture. It becomes a perfect barrier. We use this exact process now. We call it passivation. For surgical steel, spacecraft parts, anything that must stay pristine. The idea that this technique was being applied intentionally thousands of years ago. It means these artisans weren't just fighting corrosion. They were outsmarting it, using chemistry to command the material to protect itself. Then the ceramics, that delicate ringing vase. Its surface has a sheen, a smoothness deeper than polish. It carries a vitreous glaze. But this glaze is unusual. Its composition is complex, designed not just for color or shine but for fusion. It melded with the ceramic body during firing, creating a seamless, impermeable seal. Imagine a clay cup. Left unglazed, it's porous. It absorbs liquid stains, weakens, but coated in this engineered glaze and you change its destiny. You make it waterproof, sterile, easy to clean. You extend its life from seasons to centuries. This wasn't merely decoration. It was a functional upgrade, a calculated improvement to performance. These surface treatments show a mindset focused on longevity. The goal wasn't just to make an object. It was to make an object that would endure, that would resist time and environment. Building resilience from the outside in. This transforms the artifacts from relics into something more. They become testaments to a philosophy, a belief that human creation could be made permanent. That through knowledge of materials and reactions, you could defy entropy for a while, applying the earliest forms of materials science not for a temporary advantage but for a legacy. So the picture is complete, a science of combination, a science of internal training through heat, and a science of protective sealing, a holistic engineering discipline. But knowledge like this advanced and systematic, it doesn't come from nowhere. It needs a foundation, a supporting structure of society, trade, communication, which leads to the question: if they knew all this, what kind of civilization did they truly build? And why did that knowledge go out? The chamber's layout told a story. This wasn't just a room for finished work, it was a workspace, a kind of lab, and off to the side in an alcove you could see how it worked. That's where the real clues were, not polished objects, but the raw pieces, bags of mineral powders, each a different color. Some of ore, some broken up, some sorted, small hearths built into the walls with clay flues designed to pull air through. This was set up for testing, for process. Everything was methodical, it felt systematic. You could trace the steps, take ore from a specific pile, grind it into powder, mix it with another powder, a measured amount, into a crucible, then into one of those hearths where a controlled draft from a bellows would raise the temperature to a specific point. Then you'd wait, let it cool. Examine it, see what you got. A new alloy, a new glaze, a glassy slag. You'd check it. Was it harder, more flexible? Did it shine? Did it ring? So it was trial and error, but error with a point. Every failed test, every cracked ingot was a lesson, a step toward a formula. And how did they record the formulas? Not on clay tablets, not here. Their records were the objects, the successful ones. A flawless blade was a recipe for resisting corrosion. A singing vase was a recipe for strength. Those pieces in the main chamber weren't just treasures. They were the final, perfected entries in a logbook, the result of thousands of tests done right in that alcove, which changes what the tomb means. For this person, whoever they were, this sealed space wasn't just a burial. It was an archive, a library of material science written in metal and clay. Their life's work encoded not in words, but in the substances they'd learned to control. Buried with their greatest discoveries, the physical proof of their dialogue with the elements. That suggests a culture that valued that knowledge enough to bury it with its master. But it also raises a question. When they sealed the tomb, did they seal the entire school of thought with it? Did the library close before anyone could copy the books? The sealed chamber was a perfect riddle, objects that explanation but left with no instructions. To understand that lost science, we had to become detectives. Modern researchers couldn't just cut the dagger open, couldn't shatter the vase. The artifacts were too precious. Their secrets were too fragile, so the workshop became a crime scene. They used tools the original artisans could never have imagined. They brought in neutron beams. Neutrons pass through most metals easily, but they interact with the nuclei of specific atoms. Scanning the dagger with this invisible light created a three-dimensional map of its internal composition. They could see without touching it where the nickel and chromium were concentrated. They could spot microscopic voids, inclusions, signs of how the metal had been worked. That was the first word in a new dialogue, a conversation across. Spectroscopy gave another vocabulary. By shining different wavelengths of light at the singing vase, instruments could read the unique fingerprint of the elements present. They could distinguish the base clay from the complex glaze, measure their thickness. See how deeply they had fused. Each scan was like listening to the artifact's story in its own language, a language of elemental signatures, atomic structures. Piece by piece, scan by scan, the empirical triumphs of the ancients began to translate into the precise formulas of modern materials science. We weren't just admiring their work, we were decoding their recipes. What emerged was astonishing in its sophistication. Creating that stainless blade wasn't a one-step miracle. The neutron imaging revealed a layered history within the metal. The reconstruction pointed to a deliberate, multi-stage ritual. It likely began with a carefully prepared charge in the crucible, iron ore, plus specific minerals rich in chromium and nickel. The furnace would have been brought to a searing heat, far beyond what was typical for ordinary iron, sustained by a powerful, directed draft. But the real magic happened after the pour. The analysis suggested the hot metal wasn't simply left to cool in a mold. It was subjected to a series of precise thermal treatments, heated to one critical temperature to homogenize the alloy, then cooled rapidly, perhaps quenched in warm oil or a specific brine solution that would lock in hardness. But the process wasn't over. Microscopic stress patterns hinted at a final, lower temperature reheat, a tempering cycle to relieve brittleness. To achieve the perfect balance between rigidity and resilience, even the surface told a tale of process. Spectroscopy detected trace organic compounds bonded to the metal's outermost layer. This wasn't dirt, it was evidence. The most plausible explanation is that the finished blade was treated with a controlled chemical bath, maybe a solution from plant tannins or mineral salts. This wasn't just polishing, it was a deliberate passivation treatment, forcing the surface atoms to rearrange into that ultra-thin impervious oxide shield, the final defiant step against time itself. So the story reverse-engineered from the metal is one of profound patience and control. It reveals artisans who understood materials as a sequence of states, solid to liquid through the crucible, then a trained solid guided through a gauntlet of heats and cools, and finally an armored solid, its skin chemically commanded to defend the whole. This was no accident. It was a choreography of transformation, each step designed to elicit a specific property from the stubborn heart of the earth. To hold that dagger is to hold a captured symphony, fire, chemistry, and intent. But if the process was this advanced, this systematic, it forces a new thought, an unsettling one. This knowledge didn't exist in a vacuum. It required a support system, a network, which means the sealed tomb of one master might be just a single chapter in a much larger and now completely missing library of human achievement. That sealed workshop starts to feel less like a strange one-off and more like part of a bigger story. A story that's scattered all over the map, because you see these flashes, moments where material seems impossible. The Romans, for instance, they're concrete, we know concrete. We know water gets in, it freezes, it cracks. Roman concrete in their harbors did the opposite, it got stronger. Water would seep in and it would trigger a reaction. New crystals would grow, filling the cracks from the inside. The flaw became the repair. That was a living material, a kind of resilience we're only now learning to match. Then there's Damascus steel, from India, from the Middle East, blades that could cut a scarf in the air yet slice through armor. They had these watery patterns on the surface, a fingerprint. The secret was in the ore-specific trace elements and a forging process of folding and cooling. That process created carbon nanotubes inside the metal, thousands of years before we had that word. The knowledge faded when the ore sources faded, when the guilds that knew the technique disappeared. And in the Americas, the Moche in Peru, they practiced mercury gilding. They'd apply a paste of gold and mercury, then heat it. The mercury would vaporize, which is incredibly dangerous, leaving a perfect, thin film of gold bonded to the surface. An early form of vapor deposition, the same principle we use now in electronics. So you have these peaks, a local summit of material science, Roman concrete, Damascus steel, molecular gilding, and each summit was, for a long time, isolated. The Roman recipe was lost after the empire. The full art of the steel vanished. The Moche methods faded with their culture. That's the pattern. The drive to transform material is a deep human impulse, but the knowledge is fragile. It lives in the minds of masters, in guild recipes, in trade routes for specific ores. When a civilization contracts, when trade collapses, when a master dies without an apprentice, that summit is abandoned. The path up the mountain is overgrown. The knowledge doesn't just regress, it vanishes. It becomes a legend, a mystery for a future age to find. Our tomb fits right into that cycle. Another lost summit, another peak of understanding, reached through generations, then sealed away by time. So the question changes. It's not how could they do this, it's why does this keep happening? It suggests our ingenuity often outpaces our ability to preserve what we learn. We're brilliant at discovery, sometimes forgetful in its keeping. Which makes you look at our own world, our silicon chips, our carbon composites, and you wonder, what are we building now that someone someday will hold in their hands, completely baffled by how we ever knew to make it? The keys to this science weren't held by kings. They weren't held by generals. They were in the hands of the artisans. Knowledge lived in the quiet of the workshop, away from palaces. It was a sacred trust. It was the domain of families, of guilds. Lineages of masters spent lifetimes in dialogue with fire and metal. Their understanding wasn't a set of written formulas. It was a living tradition, passed from mentor to apprentice in the forge light. A master would show the precise color of the flame for annealing. The apprentice learned the sound of the hammer that meant the grains were aligning. This knowledge was written in muscle memory, in sensory intuition. It was an oral encyclopedia whispered across generations, and it was guarded fiercely. A guild's secret alloy recipe, its unique quenching medium. These weren't just trade advantages. They were the source of identity, of prestige, of a family's legacy. That secrecy was a double-edged sword. It protected the knowledge from rivals. It let deep, localized expertise flourish. But it also made that knowledge incredibly fragile. It existed only in the minds and hands of a select few. Their craft was more than technique. It was a cosmology. The right temperature for casting might be linked to the position of a star. Quenching a blade might come with a chant to a god of earth or fire. The material transformation was a spiritual event, a collaboration with the elements. This holistic view blended the practical and the profound. It meant the artisan wasn't just a technician. They were an intermediary, translating cosmic order into tangible form. That ritual context gave the work meaning. But it also wrapped the technical steps in layers of ceremony and taboo, which made the knowledge even more opaque, even more dependent on the unbroken chain of initiation. So the strength of the system was its depth. The master knew not just the how but the why, framed in the stories and beliefs of their people. The fragility, though, was absolute. If a society was disrupted by conflict, if trade routes for special ores were cut, if a master died suddenly without passing on that crucial, unwritten step. Ain snapped. The knowledge didn't gradually fade, it vanished, in an instant. A library of material wisdom built over centuries could be extinguished in a single generation. The sealed tomb we found, that might have been the final act of such a guild, burying their greatest achievements with their last true master, because there was no apprentice left to inherit the flame. The workshop became a mausoleum for an entire school of thought. This pattern, brilliant, isolated peaks of knowledge followed by silence. It makes you wonder about our own age, our open science, our digital archives. Are we at last building a summit that won't be so easily abandoned? The Dagger's perfection is a kind of silence. It tells you what was achieved, but then you have to ask, why did the conversation stop? If this knowledge was so powerful, so advanced, why wasn't it the foundation for everything that came after? Why did it have to be rediscovered later in a sealed tomb? The science didn't fail, the materials worked. Something else broke, and the fracture wasn't in the metal, it was in the world around it. First, the raw ingredients. These weren't simple recipes. They depended on very specific ores, minerals with just the right trace elements. The chromium for that stainless blade probably came from one rare, localized deposit. A single mine worked for generations. And then what happens when that vein runs out? The guild's entire library of formulas becomes a book you can no longer read. You have the instructions, but you're missing a key ingredient. Without that specific ore, you can't recreate the magic. The knowledge becomes theoretical, a legend about a metal that never rusts with no way to make it real again. So the craft isn't lost through ignorance, it's lost through scarcity. The map remains, but the treasure is gone. Then there's the social fabric. This was guild knowledge, tightly held, passed within families or closed circles. It survived through stability, through the uninterrupted succession of master and apprentice. But history isn't stable. Conflict, migration, the collapse of trade networks. These events scatter people. They disband the guilds. They break the chains of transmission. A master might flee with his life, but without his workshop, his crucibles, his community of peers, the knowledge withers. It becomes a memory of a technique, lacking the context, the tools, the collective intuition to execute it. The science was a living thing, and when its ecosystem was disrupted, it couldn't survive alone. There's another possibility. The knowledge may have become a victim of its own ritual. Remember, this craft was intertwined with cosmology and ceremony. The practical steps were wrapped in sacred practice. Over time, the why of the ritual could overshadow the how of the chemistry. The focus might shift from the precise temperature needed to perfectly performing the chant that accompanied the quenching. The practical core could become obscured by layers of esoteric meaning. The recipe survives as a rite, but its engineering heart is forgotten. The object is still made, but the understanding of why it works fades. The technology becomes a tradition and then a mystery. And finally, think about success itself. These were engineered materials built to last. That dagger didn't need replacing. That singing vase could be used for a lifetime, then passed down. When you create things of such enduring quality, you don't need to make many of them. The demand for new masters, for new apprentices to learn the full complex craft dwindles. The need to practice the art fades. A few specialists remain, treasured but rare. Then one day there are none. The craft doesn't die from failure. It atrophies from a lack of necessity. It's a quiet exit. The workshop is closed not in anger but in obsolescence. The final master passes and there is no one left to take up the bellows. So the loss wasn't a single event, it was a convergence. The depletion of a special resource, the unraveling of the social structures that nurtured the knowledge, the slow drift of practical technique into opaque ritual, and the ironic consequence of creating things too good to need frequent replacement. The science was abandoned by the flow of history. It wasn't overthrown. It was gently, incrementally left behind. Which makes you look at the sealed tomb not as a tragedy, but as a snapshot. A frozen moment of peak understanding, preserved just before the current of time swept that particular branch of human ingenuity away. It forces a humbling realization. Our technological lineage isn't a straight, unbroken climb. It's more like a forest. Towering trees of knowledge can rise, dominate the canopy for an age, and then fall, leaving only their seeds, or in this case their fruits, scattered in the dark soil for someone else to find much later and wonder at the giants that came before. The past isn't a museum, it's a laboratory. The principles from that sealed workshop are starting something in modern labs. This isn't about copying old things. It's about learning from old wisdom. There's a term for looking to nature for design, biomimicry. Now they're looking to history. The goal is to find simpler answers to our own material problems by studying what's already lasted for thousands of years. Take that dagger's perfect surface. Its corrosion-resistant layer, formed through a simple chemical bath, is a piece of nanoscale engineering. Researchers are using electron microscopes to map its atomic structure. They want to see exactly how that ultra-thin shield bonds to the metal. The insight is deep. Today we make similar protective coatings for medical implants, for artificial hips and knees, for ship hulls. But our processes use complex vacuum chambers, toxic chemicals, a lot of energy. The ancient method suggests another path. Could we design safer passivation treatments from these old recipes? Could a plant-based solution make a better coating for an implant? The research is asking these questions now, using the past as a blueprint. Then there's the ceramic, that singing vase, so strong and so thin. Its secret was the purity of the clay and the precise control of the firing. Modern high-performance ceramics are incredible. They're in jet engines in body armor, but they often need furnaces at staggering temperatures for days, consuming vast energy. The ancient artisans got remarkable strength without that industrial power. They worked with what they had. They mastered the variables they could reach, the clay's composition, the airflow in the kiln, the cooling rate. Scientists are studying these lower temperature pathways now. Could we redesign our processes to use less energy by applying these older, more patient principles of thermal control? The goal is strong, durable materials without the colossal carbon footprint. The past shows it's possible. This shift in thinking might be the greatest gift from that tomb. It challenges an assumption of our age, that advanced performance has to come from the most complex, high-tech, energy-hungry process we can build. The artifacts from the sealed workshop stand against that. They show that profound material mastery can come from deep observation, from empirical refinement, from a harmonious use of natural resources. It's a philosophy of elegance over brute force. The ancient engineers didn't have unlimited power, so they cultivated unlimited cleverness. They optimized their world. For modern researchers, these finds are more than curiosities. They're alternative data points in the grand experiment of human ingenuity. They show there's often more than one route to material breakthrough. Sometimes the road not taken, the path history forgot, holds the key to a problem we face now. By reopening that sealed workshop, we haven't just uncovered a lost science. We've gained a new collaborator in building a better, more sustainable world. The dialogue with those ancient masters is open again. This time we're listening not just with wonder, but with a notebook in hand. Among the polished blades and the ringing vases, there was this one object, a ceremonial headdress, ornate, delicate. But when a researcher picked it up, the weight felt wrong. It was too light, it felt like hardened fabric. And looking closer, you could see why. It wasn't carved from wood or stone. It wasn't solid metal, it was a weave. A lattice of these fine, hair-like ceramic fibers, all bound together in a thin clay matrix. To us now, that's recognizable. It's a primitive version of what we call a ceramic matrix composite, the same class of material used in spacecraft nose cones, in jet engine turbine blades, materials made to withstand searing heat while staying incredibly light. The ancient version was less strong, of course, but the principle was the same. And finding it there in that tomb, it's a lesson in targeted problem solving. The artisan's challenge was clear: create a ceremonial object of great beauty and symbolic importance. It needed to be rigid to hold its elaborate shape. It needed to be durable to survive. But it also needed to be wearable. A heavy stone crown is a burden. A lightweight one is a symbol of grace, of authority. So the material itself had to solve that. How do you get rigidity without the weight of solid material? The answer was to reimagine ceramic. Instead of a solid block, they made a fabric. They took locally sourced minerals, maybe an asbestos-like fiber or a specially prepared clay thread, and they wove them or laid them into a lattice. That lattice was then impregnated with a slurry of finer clay, a binder. Then came the firing. That was the most delicate step. The heat had to be high enough to sinter the clay matrix to fuse it solid, but not so high that it melted or degraded those delicate ceramic fibers inside. It was a balancing act. The result was a hybrid. The clay matrix gave the rigidity, the solid form. The network of fibers running through it gave toughness. They acted like reinforcement bars in concrete. When a stress hit the material, the fibers would absorb and distribute that energy, stop a clean fracture from spreading. It could bend slightly, dissipate force, and stay intact. That's the very definition of a composite material. Two different substances combine to create new properties that neither has alone. This case, it cuts to the heart of that lost engineering mindset. It wasn't about showing off with the most impressive material possible. It was about designing the perfect material for a very specific need. The headdress needed low weight, high rigidity, ornate. A solid metal casting would be too heavy. Carved wood would be too fragile. Plain ceramic would be too brittle. So they engineered a solution. They looked at their available resources, specific minerals, clay, their controlled kilns, and they combined them in a novel architecture. They moved from working with materials to designing new materials from the ground up, or from the fiber up. This approach mirrors the most advanced engineering now. When aerospace engineers need a material for a rocket nozzle, they face a similar, more extreme paradox. It must withstand temperatures that melt steel, yet be as light as possible to save fuel. Their solution is ceramic matrix composites, silicon carbide fibers in a silicon carbide matrix. The ancient headdress is a direct, humble precursor to that, a proof of concept that the composite philosophy, building materials with designed internal structures, is a powerful, timeless tool. It shows these artisans weren't just technicians following recipes, they were designers. They understood that the function of an object begins not with its shape, but with the very substance it's born from. By solving the material equation first, they liberated the form. That lightweight, fracture-resistant crown wasn't just an artifact. It was a triumph of applied materials science. A quiet testament that some of the most elegant solutions come not from unlimited resources, but from a clear understanding of a problem. And the creative will to weave a new answer from the threads of the old world. The headdress was an engineering marvel, but it was more than that. The material itself was a message. That's the final layer to understand that lost science. The mastery over materials wasn't just about utility, it was driven by meaning. The workshop was a temple, transforming matter was a spiritual act. Look at the colors they achieved, that blade that wouldn't corrode with its mirror finish. It wasn't just stainless. It was a piece of captured sky, captured moonlight. In their view, a metal that resisted decay wasn't just practical, it was a physical metaphor for eternal power. For an authority that would outlast a single lifetime. The sheen was a symbol. Or the resonant vase, the one with a clear, ringing tone when you struck it, that wasn't an accident from thin walls, it was designed. In ritual, that sound could have been the voice of the divine, channeled through crafted earth. The material was made to sing. To bridge the human and the sacred. This symbolic drive changes everything. It explains why they pushed so far, creating perfectly clear glass or a pigment of unmatched brilliance that wasn't about aesthetics, not in a modern sense. It was about capturing light, the essence of the sun god. Forging a blade that never tarnished was an attempt to make mortality bow to human craft. The quest for the perfect material was a philosophical pursuit, a religious pursuit. They were trying to manifest abstract ideals, purity, permanence, connection to the divine into tangible form. Think of the alchemists later on trying to turn lead into gold. Their goal wasn't just wealth, it was spiritual transformation, the perfection of matter mirroring the perfection of the soul. These ancient material engineers were doing the same profound work, but with stunning practical success. Their laboratory and their temple were the same room. The furnace fire was both a tool and an offering. Quenching a blade in a special liquid wasn't just a heat treatment, it was a baptism, a ritual death and rebirth for the metal. This fusion solves a puzzle. It tells us why such advanced knowledge could be so fragile, so secretive. This wasn't public technology, it was sacred mystery. The recipes were rituals, the process was a liturgy. To share it carelessly would be sacrilege. The knowledge was protected not just to guard a trade, but to guard a holy rite. And it explains why, when the cultural context shattered, when the gods were forgotten, the rituals abandoned, the technical core lost its reason for being. The how was inseparable from the why. Without the spiritual imperative to create a vessel for a god's voice, why spend a lifetime perfecting the recipe for a singing ceramic? The science faded because its deepest motivation was extinguished. So the legacy of that sealed workshop is two things. It shows us astonishing technical prowess, yes, but more importantly, it reveals a worldview, where humanity's dialogue with the material world was a sacred conversation. They didn't see inert matter, they saw potential spirit. Their greatest creations were attempts to answer the biggest questions, not with words, but with the substance of the earth. In their hands, engineering became an act of reverence. And that might be the most profound lesson they left behind, waiting in the silence for us to finally hear. The headdress was more than an object, it was a question, and archaeology had to change to answer it. For a long time, the approach was straightforward. Archaeologists were the main investigators. They would dig, document, and recover things. Later, those finds might go to a lab. The object itself was the prize. Its context mattered. But the invisible story, the one in its molecular structure, often wasn't read until it was too late. The sealed tomb broke that model. When they saw that blade, they knew this wasn't just a puzzle for history. This was a problem for materials science. And if you treat a 2,000-year-old alloy like a simple artifact, you destroy the data you need. The old way risked losing the answer while trying to find it. So a new method came from necessity, a truly interdisciplinary approach. From the first day, the team wasn't just archaeologists. It was chemists, metallurgists, materials engineers. They entered the tomb together. The conversation started right at the door. This materials first idea changed everything. It meant extraction became a delicate, collaborative surgery. Before lifting an object, the team would talk it through. How do we move it without disturbing the microscopic residues on the surface? Those residues, a hint of quenching oil, a trace of polishing compound, were now primary evidence, not dirt to be cleaned off. So they developed new techniques. Instead of brushing something in the field, they might use a fine static-free film to gently lift and preserve the dust right from the surface, sealing it for the microscope later. They sampled the very air in the chamber, captured it in canisters, to analyze for ancient particulates from the workshop's last firing. Every action was meant to collect data, not just an item. This shifted the value of everything they found. On a traditional dig, the piles of slag, the broken crucibles, the ash, that was often recorded as workshop debris and then discarded. It was context, not treasure. But to this new team, that slag was a frozen moment of process. Its glassy texture could tell you the peak furnace temperature. Its chemical composition could point to the specific ore recipe used that day. A broken crucible wasn't trash, it was a text. Its interior walls held a record of repeated thermal stress, a diary of the heats it had survived. These materials became the core of the story. The beautiful finished dagger was the climax, but the slag and the broken tools were the entire plot, written in a language of chemistry and physics. This required a fundamental revision of field practice. Excavation grids got finer, sampling became more meticulous. The goal was no longer just to find beautiful things. It was to reconstruct the lost workshop as a functioning laboratory. And to do that, you needed to preserve every clue, even the ones you couldn't see. The tomb taught a humbling lesson. You can't understand a culture's true sophistication by only looking at what they chose to display. You have to look at how they made things. You have to examine the very fabric of their creations with a scientist's eye. Their technological intelligence is embedded in the grain of their metals, the matrix of their ceramics, the residue of their experiments. To reach that intelligence, the archaeologist can't work alone anymore. They have to be the conductor of an orchestra of experts, all reading from the same score. A score written not on parchment, but in the transformed matter of the ancient world. This collaborative lens doesn't just show how an object was made. It starts to show the thought process behind it. The choices, the failures, the breakthroughs. It turns a static artifact into a dynamic record of human problem solving, and it raises a bigger question. If we apply this new forensic eye to other sites, what other lost sciences might we find waiting, hidden in plain sight in the materials themselves? When something doesn't fit the timeline, you look for an explanation outside of it. A blade that doesn't rust, a vase that sings, a headdress made of materials that shouldn't exist. They're so advanced, so out of place that a story forms. Maybe visitors from the stars, or a lost civilization with impossible technology. It's a dramatic story, but it does something. It takes away our ancestors' greatest achievement, their own ingenuity. The evidence from the sealed workshop tells a different story, a more remarkable one. It wasn't delivered from above. It was built, piece by piece, right here. Look at the tools they left, crucibles worn thin from use, stone anvils grooved from hammer blows, small hearths for testing. These aren't relics of alien tech, they're human scale, instruments of discovery. They show a process. In the layers of the site you can see it. The earliest ceramic fragments are thicker, more porous. As you move up through the strata, the shards get thinner, the glazes more complex, the colors more stable. It's a visible record, trial and error. Incremental improvement over generations. This isn't the signature of a sudden gift. It's the fingerprint of a long conversation with the material world. Power of this discovery isn't improving something supernatural. It's in revealing what ordinary people could do. These artisans worked without modern labs, without theoretical physics. Their genius was empirical, built on observation. They noticed ore from one hillside gave a different metal than ore from another. They saw quenching a blade in one liquid made it harder than another. They found adding a certain ash to a glaze changed its color, its durability. Each observation was a data point. Each failed experiment, each cracked ingot was a lesson. Over decades, over centuries, this knowledge accumulated. It was refined. It became a science of materials passed from master to apprentice, honed to a breathtaking peak. This narrative isn't less amazing than the alien theory, it's more so. It credits our ancestors with the intelligence, the curiosity, the perseverance to unlock nature's secrets through their own faculties. They looked at the world, at rocks, clay, fire, and they asked, what can this become? Their answer was a testament to human potential. To suggest otherwise, to hand their accomplishments to some outside force, diminishes one of the most inspiring chapters in our history. The sealed tomb doesn't point to visitors, it points to us, to what we're capable of when curiosity is given time, cultural support, the freedom to experiment. The legacy of that workshop is a message. It says profound innovation doesn't require magic, it requires attention, patience, the courage to try again. And that truth is far more powerful than any myth, that perfect surface on the blade. It's a paradox. To learn its secrets, you have to risk destroying them. That's the quiet tension in archaeology now. A real ethical question right there in the dust. How do you balance wanting to know with the duty to protect? Because the act of studying it, taking a sample, letting in modern air, even too much light, it changes the artifact, for good. You might get a data point, but you lose a piece of the original story. And that story isn't just ours. It belongs to everyone who comes after, so you have to ask, what do we owe the future? Do we use up the past to understand it, or do we leave it alone, leave its mysteries for someone else with better tools? That dilemma created a new principle, minimal intervention. The idea is to do as little as possible to the object, like a medical oath. First, do no harm. It changes the whole process. Before you ever touch it, you use every non-invasive method you have. Laser scanning maps the surface in microscopic detail. You get a perfect digital copy. Advanced imaging like neutron scanning looks inside without a scratch. Spectrometers read its elements from a distance. The goal is to get all the data before you even think about using a tool. But sometimes a tiny sample is the only way to answer a big question. That decision is never easy. Panels of experts debate it, archaeologists, scientists, conservators, cultural representatives. They argue, is the knowledge worth the permanent loss? If they go ahead, it's with surgical precision. The sample is the absolute minimum, maybe a microscopic piece from a spot that's already damaged. It's a calculated compromise, a small sacrifice for understanding, documented in extreme detail so future researchers know what was taken and why. And that leads to maybe the most powerful tool now, digital preservation. You combine all the scans, the spectral data, the 3D models. You create a virtual artifact that's often more informative than the physical one. A researcher anywhere can examine the digital twin, measure it, analyze it, run simulations on how it was made, all without the original ever leaving its case. The physical object becomes an anchor, preserved as close to its discovery state as possible. Its digital copy becomes the workhorse for study. This doesn't just protect the artifact, it opens access. Anyone anywhere can explore a perfect model of the singing vase or the headdress. So the sealed tomb teaches a lesson beyond material science. It shows our responsibility goes past discovery. It includes stewardship. The real legacy of that ancient workshop isn't just the knowledge we take now. It's making sure these silent teachers remain for centuries, ready to tell their stories with methods we haven't even imagined. We're not just interpreters of the past, we're its curators. And that role needs a humility to match our curiosity. The detective work is just starting. With this new lens, the search has widened. Archaeologists aren't just looking for tombs full of gold anymore. They're hunting for workshops, for ancient laboratories. The clues they follow are subtle, but they're there. They go back to known sites, places once called simple settlements or burial grounds, and they ask different questions. Where are the slag heaps? Not just any debris, but specific glassy residues that point to sustained, high-temperature work. They ask what minerals are in the local geology. Is there a source of chromium or nickel or rare earth elements nearby that could have supplied a specialized craft? They scour ancient texts, not just for kings, but for passing mentions. A poet's reference to a sword that never dulled. A merchant's record of a translucent cup that rang like a bell. These aren't just metaphors now. They're potential reports, field notes from a lost science. The methodology on the ground is changing too. Geophysical surveys using ground-penetrating radar, they scan not just for grand structures, but for the footprints of industry. They look for the outlines of furnaces, for clay-lined pits that could be quenching tanks, for workshops built right next to the tombs of elite individuals. The reasoning is clear. If one master artisan was buried with their life's work, others may have been too. The goal is to find more of these sealed time capsules. Not to loot them, but to listen. To let each one add another sentence to this fragmented manuscript of a global tradition. Because the emerging picture suggests this wasn't an isolated event. It was a pattern, a peak of material understanding that could arise in different cultures at different times when the conditions were right. A stable society, a guild system, access to specific resources, a cultural drive to imbue matter with meaning. When those stars aligned, a local summit of engineering could be reached. In the Andes, with platinum alloys worked at temperatures that should have been impossible. In South India, with the legendary Wootz steel that made Damascus blades. In China, with their early porcelain and sophisticated bronze alloys. Each might represent another branch of the same vast, disconnected tree of human material science. So the quest becomes a global puzzle, a detective story across continents, and each new site with unusual residues, each artifact with inexplicable properties, is a potential dot on a map we're only now learning how to read. The hope is to find enough dots to trace the outlines of a forgotten network, not of trade in goods, but trade in ideas. The slow, precious migration of techniques and recipes along ancient routes. Did a concept for passivating metal travel from one valley to another? Did a recipe for a resonant glaze inspire a potter 1,000 miles away? By connecting these technological dots, we might finally see the contours of a conversation. A worldwide, if intermittent, dialogue about how to transform the very substance of the world. And in doing that, we honor not just the objects, but the brilliant, patient human minds that made them. This discovery changes more than a museum display. It changes how we teach. For generations, textbooks told a clean story, a steady upward line on a graph, from stone to bronze, from iron to steel, from steam to silicon, a comforting story of constant advancement. But the artifacts from that sealed workshop, they draw a different picture, a jagged line with peaks and valleys. They introduce this idea into education, the idea of lost peaks, periods where a technology in a specific place reached a sophistication that was later abandoned, forgotten, only to be relearned centuries later. This isn't a minor footnote. it's a fundamental shift. It teaches students that innovation isn't inevitable, it's fragile. It depends on an ecosystem: resources, stable society, cultural motivation, the unbroken transmission of knowledge. When that ecosystem breaks, the peak is lost. The line on the graph doesn't just plateau, it plummets. That workshop becomes a valley of silence on the timeline. This nonlinear view is more honest, and it's more inspiring. It shows that brilliance isn't exclusive to the modern age. It has flashed throughout our past. It challenges the assumption that older means simpler. A student holding a replica of that stainless dagger is holding a contradiction. It forces a question. If they could do this then, with so little, what does that say about human potential? This approach weaves disciplines together. The story of that blade isn't just a history lesson. It's a chemistry lesson about alloys and corrosion. It's a physics lesson about heat transfer and grain structures. It's an engineering lesson about problem solving with limited resources. It shows that to understand our past, you can't just study dates and battles. You have to study materials. You have to see how the substance of their world, their ceramics, their metals, holds the record of their thoughts. Their ingenuity. This lens makes learning dynamic. It connects abstract formulas to the tangible triumphs of human culture. It frames history not as a parade of events, but as a conversation. A continuous, often interrupted conversation between humanity and the material universe. By teaching these lost peaks, we give students a more complete story, a more humble story, a more fascinating story of who we are. We show them that progress isn't a straight road we walk forward. It's a landscape we explore, sometimes climbing high, sometimes losing the path, and sometimes finding the footprints of those who climbed before us, pointing the way to heights we thought were ours alone to discover. That master's entire career is told through materials. You can follow it in the layers of the workshop. The earliest crucibles, down at the bottom, they're cruder, thick walls, uneven glassing. That's an apprentice learning the heat, making errors. Then you go higher. The crucibles get thinner, more refined. They can take repeated, hotter fires. That's the confidence of a master who knows exactly how the flame will move. And the final pieces, the ones carefully placed in the main chamber, those aren't just objects. They're a culmination, a life's question answered in metal and clay. This wasn't a solo effort. The workshop size, the multiple hearths, it points to a team. Probably the master worked with their children, their nieces and nephews, trusted apprentices. That knowledge was a family heirloom, more valuable than any gold. You can see it. The master's hands, and strong from a lifetime at the forge, guiding a younger pair over a crucible, explaining not just the motion but the reason. The color of the flame, that means the alloy is ready. The sound the clay makes as it cools, telling you if the firing was true. That education was a sacred trust. Each lesson was a thread in a tapestry of understanding that took generations to weave. The master wasn't just teaching a craft. They were passing on a worldview, a way of seeing potential in raw earth and a method for unlocking it. Choosing that sealed space as a final resting place, that was the most personal statement. In many cultures, what you take with you defines what you value most for the journey. A king takes symbols of power. A warrior takes their weapons. This artisan took their legacy of innovation. They surrounded themselves not with wealth, but with their greatest intellectual triumphs. The blade that wouldn't corrode, the vase that resonated, the composite headdress, these were their life's chapters. Bound in a library of transformed matter, it tells you their identity, their deepest pride was rooted in problem solving, in creating beauty through understanding, in pushing the boundaries of the possible. They were, in every sense, an engineer, an applied scientist whose laboratory was the real world. That drive feels familiar. It echoes in the modern researcher spending years on one experiment, in the engineer iterating a design for a tiny gain, in the artist perfecting a technique over a lifetime. The longing to create something of enduring value, to solve a puzzle, to leave a mark that says, I was here and I understood something, that's a thread connecting us across centuries. The artisan in that tomb isn't some alien figure from a lost age. They're a colleague, a fellow traveler on the human journey of curiosity. So the tomb's ultimate gift is that connection. It collapses time. When we study that blade with neutron scanners, we're not just analyzing an artifact. We're reading the final report of a peer. We're witnessing the conclusion of a lifetime of dedicated, brilliant work. The tomb is far more than a cache of objects. It's a biography. The autobiography of a forgotten genius of practical science, written in the only language they trusted to last, the silent, enduring language of perfected materials. And in that silence, there's a question meant for all of us. What will we choose to leave behind that speaks so clearly, so far into the future, about what we truly valued? That workshop's legacy isn't just in books anymore. Those principles are being turned into solutions now. It's not about copying old objects. It's about using old wisdom for new problems, especially sustainability. The research into these forgotten methods is producing unexpected, modern applications. The past can be a source for green innovation. Take the organic materials from the tomb. Residues on tools and within composites like that ceremonial headdress had traces of natural binders. These weren't synthetic glues. They came from plant resins, tree saps, animal proteins. Scientists analyzed those ancient formulas, broke down their molecular structure, and they found a blueprint for adhesion, strong and completely biodegradable. That research has inspired new, eco-friendly adhesives. A wood glue for furniture that holds for decades, but can be composted after. Or medical adhesives for closing wounds from natural sources to reduce allergic reactions. The ancient choice to use what nature provided is guiding a shift away from petroleum-based, permanent plastics. Then there's energy efficiency. Modern industry often uses brute force, immense heat and pressure, to make advanced materials. But the sealed workshop showed a different philosophy. Their method for creating certain glassy phases in ceramics and slags was done at remarkably low temperatures. They used precise control over chemistry, airflow, thermal cycling, not just cranking up the furnace. Now, materials scientists are exploring that low-temperature pathway. The goal is to make high-performance ceramics for electronics, engine components, using much less energy. If we can replicate their patient mastery of heat, we could cut the carbon footprint of countless products. Their approach shows advanced performance doesn't always need the most power-hungry process. Sometimes the elegant solution is the efficient one. Even the visual language of the artifacts is speaking to engineers. The geometric patterns on many objects were likely symbolic, but researchers now suspect a hidden, functional purpose. Those intricate designs could have distributed mechanical stress across a blade or a vase, preventing cracks from starting or spreading. That concept is now inspiring biomimetic design in architectural materials. Engineers are creating new building facades, structural panels, with patterns from these ancient motifs. The patterns aren't just decorative, they're computationally designed to channel forces, to make materials stronger, more resilient, with less raw substance. A 2,000-year-old decorative motif is becoming a template for lightweight, durable, modern architecture. This cross-pollination of ideas across reframes our relationship with history. The sealed tomb isn't a dead end. It's a conversation starter. Those artisans weren't just making things for their time. They encoded principles of material harmony and efficiency, principles that resonate with the needs of our time. Their drive to work with nature to optimize rather than overpower offers an alternative model for innovation. In that silent workshop, they left more than artifacts. They left a toolkit for a more sustainable future, waiting for us to learn its language and put those lessons to work. That sealed workshop. It's a quiet answer to a story we like to tell ourselves. We think of history as this climb, out of darkness into light, a steady march to where we are now, but this discovery breaks that story. It shows you a different landscape, not one mountain but many, peaks and valleys. A civilization can reach a height, a real understanding. And then the way up can be forgotten by the people who come next. If knowledge that advanced can be lost like that, then our own civilization with all its technology isn't some final stop. It's fragile, more like a garden than a fortress. Progress isn't a forward march, it's an ecosystem, a garden you have to tend. Some plants, some technologies, some sciences, they bloom for a season. They give you nourishment, structure. If the gardeners change or the climate shifts and the knowledge of how to care for them isn't passed down, those plants wither. They die back to the root. And the garden looks simpler, less vibrant. The potential is still there, in the soil, in the old seeds, but it's dormant, waiting for some future gardener to find those seeds, and with care help that particular bloom find the light again. That's the cycle, the organic nature of how we advance. Our digital age, our networks, they feel permanent. Unshakable, but that sealed tomb is a whisper, a warning. No garden tends itself, it's a humbling thought. It asks you to put aside the idea that we're at the end of history's journey. We're just the current caretakers, and it makes you ask a question, an urgent one. What are we in danger of losing right now? What essential knowledge? Our seeds aren't in clay pots anymore. They're not buried in hillsides, they're encoded in digital formats that go obsolete every few years. They're locked in silos, expert communities that don't talk to each other. They live in the muscle memory of aging craftspeople, people whose apprenticeships don't exist anymore. The recipe for a self-healing concrete might only be in a corporate database, proprietary. The skill to hand-forge a specific tool might live in one last artisan's hands. The deep wisdom of how to live in balance with a local ecosystem that might be fading from memory, replaced by generic global answers. We're brilliant at generating new seeds, but are we tending the garden of everything we've learned? Are we keeping its biodiversity, so if one crop fails, others are still there? The lesson from the dust is that preservation isn't passive, it's an active choice, a deliberate one, a choice our ancestors in one moment of silence didn't make. Their loss is our gain now, but only if we listen, and only if we learn to be better gardeners of this fragile world. This flourishing place we have, a garden, depends on its seeds. We found seeds in that sealed tomb, seeds thought extinct. From a forgotten harvest of the human mind, they're growing again now, not in soil, in the ground of our own curiosity. This find is more than an archaeological marvel. It's a mirror held up across thousands of years, and it shows two things about us. The first is the depth of human capability, those artisans with simple tools and patient watching. They reached a mastery of materials, a sophistication that rivals our own. It proves genius isn't just from our time, it's a timeless spark. It waits for the right conditions to catch. And the second thing the mirror shows is our fragility. Their peak of knowledge, hard-won, it was lost, to shifting sands, to time, to trade, to tradition. It whispers that no achievement is permanent, no matter how advanced. Our digital libraries, our networks, they're vulnerable in their own way. We went from one sealed room to the edge of modern science and philosophy. We saw how ancient empirical mastery doesn't just challenge our timeline, it inspires new paths. In sustainability, in medicine, in design. Their dialogue with the elements is now our dialogue with them. So here's a quiet reminder, to see the past artifacts not as dead things in a case, but as messages in a bottle, written in the language of transformed matter, to approach them with wonder, sure, but also with deep respect. Because they aren't just relics of where we've been, they're often signposts, pointing to solutions we haven't found yet. They might hold keys to our future, forged in the wisdom of a past we're only starting to understand.